Chapter 10 expands on what we learned in both chapters 8 and 9, except now we're dealing with 2 samples at a time instead of just 1 sample. So we'll start with this example from an episode of Mythbusters where they were trying to figure out if you saw somebody yawn, if that would make you more likely to yawn yourself. So what they did is they took a sample of 50, I believe, people, and they randomly assigned them to getting a yawn seed where the experimenter yawned in the subject's presence before they left, and then a room where they didn't yawn before they left the room. So we'll call a yawn seed something where the experimenter yawned in the subject's presence. And then we've got the control group where the remaining 16 subjects did not have a yawn. So we had 34 subjects receive the yawn seed and 16 subjects did not receive the yawn seed. So let's see what this experiment looks like if we drew a diagram. We've got 50 subjects and we randomly assigned them to 2 groups. Group 1 will be the 34 subjects who received the yawn seed, and Group 2 will be the 16 subjects who did not receive the yawn seed. And this was random assignment. Then what we did is we gave them each a treatment. So they received the yawn seed, and this group did not get the yawn seed. And once we left them in the room for a period of time to see if they yawned or not, we compared the results. So you compared their yawning proportions, the proportion of the subjects who yawned. And here are the results of this Mythbusters experiment. So we have whether or not they received a yawn seed and if they yawned. So this row right here represents they received the yawn seed. That's the first group. And this row right here represents if they did not receive the yawn seed. That was group 2. So we have 2 different proportions. So now instead of just having p hat, we're going to have p hat 1 and p hat 2. So p hat or p1 is the true proportion. Remember, that's talking about a population. The true proportion of people who, given the yawn seed, will yawn. So that is 10 out of 34, which is 0.29. And then p2 is the true proportion of people who, when given no yawn seed, will yawn. And that was 4 out of 16, which was 0.25. So the difference in the proportions was 0.29 minus 0.25, which is 0.04. So just by looking at this one sample, we might think that, oh yeah, there is a difference in yawning, whether or not you see someone yawn or you don't see someone yawn. So the next question then is, do the data provide some evidence that yawning is contagious? So people yawned more often than not when they were given the yawn seed in this sample. But we're good statistics students, and we know that just because one sample says it's true, that doesn't mean it's true for the whole population. And the reason for that is variability due to random sampling. So Adam Savage and Jamie Heineman, the co-host of Mythbusters, they used this one single sample data to conclude that yawning is contagious. And I don't know, depending on how much you paid attention in my class this year, every time you watch Mythbusters, you'll be annoyed because they always use one sample or one experiment to make a Mythbuster conclusion. And you can't always say that that's the truth for everyone everywhere. In that sample, it happened to be a myth busted or not based on that sample. But the reason you can't say it's true all the time is because there's always going to be variability due to random sampling. There's a chance that you could have gotten these results just because you randomly selected your subjects. So because of variability due to random sampling, you cannot extend these results to the entire population just yet. So based on what we just did in the previous example, that brings us to some general ideas about sampling distributions of a difference of proportions. Now, we might need to review in class about the shape, center, and variability of a sampling distribution. We learned that last semester. You might need to brush up on your Chapter 7 notes if you forgot some of this. But let's talk about the shape, center, and variability of a sampling distribution for a difference of proportions. So the shape of a sampling distribution is always going to be approximately normal as long as the conditions are met. So it's going to be approximately normal, and that's if you have large counts or if the normal condition is met. So the normal condition for a difference in proportions, you have to show that N1 P hat 1 is greater than or equal to 10, N1 1 minus P hat 1 is greater than or equal to 10. And you have to do the same thing for the second sample. It seems kind of tedious, but you'll get over it. 1 minus P hat 2 greater than or equal to 10. So all four of those must be true for you to say that the sampling distribution is approximately normal. The center, the mean of a sampling distribution is always going to equal the population parameter. So the mean of the sampling distribution of the difference in proportions is equal to P1 minus P2. And you want to make sure you have random selection for that, but we won't focus on that right now. And the variability is, in this case, we're going to use standard deviation. The standard deviation of the difference of proportions is equal to P hat 1 minus P hat 1 over N1 plus P hat 2 1 minus P hat 2 over N2. This is on the formula sheet, so don't freak out. You don't have to memorize this. And there's one other condition that always has to be met. We talked about the large counts conditions. We talked about it both being random samples. Right here to say that. And the last condition is the 10% rule. N1 and N2 should be less than or equal to 10% of the population in order for it to be a good independent sample. So let's see how the shape, center, and variability works in the context of a problem. Your teacher brings 2 bags of colored goldfish crackers to class. Bag 1 has 25% red crackers and bag 2 has 35% red crackers. Each bag contains more than 1,000 crackers. Using a paper cup, your teacher takes a random sample of 50 crackers from bag 1 and a separate random sample of 40 crackers from bag 2. So we have defined our variable here that P hat 1 minus P hat 2 is the difference in the sample proportions of red crackers. So usually you would define each variable separately, like P1 is, P2 is, and then P1 minus P2 is. You'd have to define all those variables, but we're just going to let that be the defining of the variable. What is the shape of the sampling distribution of P hat 1 minus P hat 2, and why? Well, we know that the shape is always going to be approximately normal as long as the normal condition is met. So let's check if the normal condition is met. N1 P hat 1 greater than or equal to 10, let's check that. 50, N1 is 50. So P hat 1, how many were red? 25% were red. So we'll just say P hat is 0.25. And N2 is 40. And P hat 2 will be 0.35. So N times P is 50 times 0.25, that's greater than or equal to 10. 50 times 0.75 is greater than or equal to 10. 40 times 0.35 is greater than or equal to 10. And 40 times 0.65 is greater than or equal to 10. Now the reason we had to use the population proportions here, 25% and 35%, is because the sample proportions is unknown. And if you remember from chapter 7, the whole point of a sampling distribution is you take an estimated guess of the population, and you're seeing how the samples, if you took random samples from that population, how they would be distributed around that true population proportion. So because these conditions are met, the shape is approximately normal. And my marker has decided not to work. Oh, there we go. Approximately normal. And the mean of the sampling distribution we just learned is the mu of p hat 1 minus p hat 2 is equal to p1 minus p2, which we are given in the problem. 0.25 minus 0.35 equals negative 0.10. Now, it's okay to have a negative difference. A negative difference means that the second one was bigger. So if P1 minus P2, if that comes out negative, then that means that P1 is less than P2. That's all that means. So you're allowed to have a negative difference for p hats. So now let's calculate and interpret the standard deviation. So again, the formula here is the square root of p hat 1, 1 minus p hat 1 over n1 plus p hat 2, 1 minus p hat 2 over n2. And now let's plug in these numbers. 0.25 times 0.75 over 50 plus 0.35 times 0.65 over 40. Type that into your calculator carefully and you get 0.097. And now we're going to interpret this value. You can use the same interpretation for standard deviation that we have used all year. And the general form for the standard deviation is the average distance from the mean, or the average distance from the center. So in this case, the center is the difference in proportions. So the difference in proportions will vary from the center by about 0.097. So we've got the difference in proportions typically varies from the center, negative 0.10, by about 0.097.